In 1861, Maxwell came up with a theory to describe electromagnetic radiation. It consists of a couple of main points. Number one, what causes it? What does cause electromagnetic radiation? Nick? Good, accelerating charges. Now, there's lots of little different ways in which we can accelerate charges to generate EMR, but in general, we say it's accelerating charges. Now, be careful here. If we have charged particles, they will always generate a gravitational field. Moving, accelerating, at rest, it doesn't matter. As long as they have mass, they generate a gravitational field. An electric field will always be generated by a charged particle as well. Moving, accelerating, at rest, it doesn't matter. But if it's accelerating, it'll generate a changing electric field as opposed to just a constant electric field. In addition, a magnetic field can only be generated by a moving charge. But if it's moving at a constant speed, it generates a constant magnetic field. If it's accelerating, it generates a changing magnetic field. So accelerating charges generate EMR because of what EMR consists of, the composition of EMR. Spelled it wrong. There we are. Composition of electromagnetic radiation. The composition of electromagnetic radiation is this. What could this represent? There's one of two things that this could represent. It's a wave, yeah, but specifically a magnetic field. So let's say that's a magnetic field. It doesn't really matter whether it's the magnetic field or whether it's the other one. It consists of this, and it consists of this. I'm going to give up trying to draw that now. You know what I mean by that, right? What's the other one? If the blue one is the magnetic field wave that's changing, then the green one is the electric field wave that's changing. Right? Accelerating charged particles generate changing electric and changing magnetic fields, whereas just moving charges generate constant electric fields and constant magnetic fields, and that's not enough to have electromagnetic radiation. Now, what do we know about those two fields? Relative to one another, that is. So they're in phase with each other. So when you've got a crest, you've got a crest. When you've got a trough, you've got a trough. Good. What else do we know about them? Big word. Okay, it's a big word that carries throughout this unit. Yeah. They're perpendicular to each other. Okay, if you're ever dealing with a direction in this unit, it's probably going to be a perpendicular direction. Okay, if in doubt, go perpendicular. Okay, so if one's on the x-axis, one's on the y-axis, if one's on the x-axis, the other's going to be on the y-axis or the z-axis. If one's on the z, the other one's going to be on the x or the y-axis. What do we know about the direction of propagation or the movement of these two fields? What do we know? Listen carefully to what I just asked. What do we know about the direction of movement of these two fields? If in doubt, go with perpendicular, right? If one's on the x, one's on the y, it's going to move on the z-axis. If one's on the x, one's on the z, it's going to move on the y-axis. So this electromagnetic wave would travel either this way, or you could say that it was traveling this way, but bottom line is it's perpendicular to both of those waves. Does that make sense? All right. Good. There were 4 things that we learned about yesterday that provided support for the wave theory of EMR, Maxwell's wave theory of EMR. 4 properties of waves that EMR exhibits or that EMR shows. What were those 4 properties? What's one of them, Quinn? Diffraction. Quinn, what's diffraction? Yep. Yeah, good. When a wave goes through an opening, it spreads out. Or when a wave goes around a corner, it will also spread out, right? Good. Diffraction's 1. Matt?
Refraction.
Good. What's refraction, Matt?
When it goes through a medium and bends.
Yeah. So when we go from one medium to another, the speed of the wave changes, and as a result of that speed changing, then the direction also changes. Good. So refraction is another one. Yep, Spencer? Interference, which sometimes goes with diffraction, sometimes not. Interference occurs when you have 2 waves or 3 waves or 4 waves, whatever, encountering each other at the same time, producing either a bigger wave or a smaller wave, constructive or destructive interference. And the 4th one is, Sherry? Polarization, which is the one that we learned about yesterday. You'd heard of it before yesterday probably, but you might not know what it was. That's the filtering out of all the components of a wave except one. So if we filter out everything except horizontal, we polarized it horizontally. All four of these are properties of waves. Since they're properties of waves that are exhibited by electromagnetic radiation, or that EM radiation shows, then we must have EM radiation as a wave. Right? Prior to 1861, like, there was debate, right? Some people thought it was a wave, some people thought it was a particle, and opinion shifted, and it was, like, some people argued because of this that it's a wave, some people argued because of that it's a particle, whatever. But finally, in 1861, looks like we have some closure on this, right? It looks like we have like firm data showing us that we've got a wave here. But we're going to learn later on in our unit that there is evidence to support the particle nature of EMR as well. We're not going to take away this. Okay, what I'm teaching you now is still going to be correct. We're just going to add to it later on in the unit and say, yeah, it's a wave, but yeah, it's also a particle. It's got kind of a dual nature, a wave-particle duality. We'll talk about that more a little bit later on. All right, let's look at the 7 types of EMR. You think back to the song that we played a couple of times already. What's the first kind? Radio waves, yeah. Microwaves, okay. And then we've got, what's the next one? Infrared. Infrared, infra meaning below, red, obviously, infrared. So, of course, right above infrared we'll go red, which consists of, or which is a component of visible light. Roy Jabiv. What's above violet? Ultraviolet. And above ultraviolet would be X-rays. And then, of course, at the end, we've got gamma rays. There are unique ways of generating each of these types of EMR. Like, when it comes down to it, it's accelerating charges one way or the other, but the specific mechanism is a bit or dramatically different for each of these types of EMR. Radio waves and microwaves usually come together. They're both produced by, generally, yep, oscillating charges. What does oscillating mean, Brendan?
Back and forth.
Yeah, electric charges that are going back and forth. Now, as they're going back and forth, back and forth, back and forth, they got to speed up, slow down, change direction, speed up, slow down, change direction, and so on, right? Accelerating charged particles. Yep.
Does that mean they're moving back and forth, like going back and forth between the charges, like being constantly
No, that's a good question, actually. It means they're moving back and forth, physically moving back and forth. Now, sometimes it's just within a wire, sometimes it's a little bit more complicated than that, but the electrons is still, in any case, the electrons or whatever charge it is, in any case, is moving back and forth, not changing charge. Okay, we can't change an electron to a proton. Okay, but we can move an electron back and forth, or in certain circumstances, a proton back and forth as well. All right, infrared, visible light, and ultraviolet, they all go together. They're all produced by, yep. Yeah, different transitions, like they're all different transitions, but still, in general, we say electron transitions in atoms. Now, in all cases, if we're generating each one of these types of EMR, it's got to be a transition from a high level to a low level, right, as opposed to the other way around. You guys are going to learn later on in the year, and some of you have already learned, probably in chemistry, that electrons can make transitions from lower levels to higher levels as well, right? That doesn't generate EMR. Okay, that has to absorb energy to do that. To give off energy, we're going from high level to low level. All right, X-rays are generated by, occasionally by electron transitions, actually, but usually by accelerating electrons, yes. Be more specific there, though. Rapidly decelerating electrons. So what we do is we accelerate them to an incredibly high speed. That's not the production of EMR, though, accelerating them to incredibly high speeds. When we get them to a high speed, we smash them into a target, and the rapid deceleration, the almost instant deceleration of these electrons causes the kinetic energy to be dissipated as light energy, photon energy. So ultimately, we're accelerating electrons across potential difference to a really, really high speed, and then that kinetic energy gets transformed into another kind of energy that we call light energy. Now, I'm not going to give you the equation that describes the light energy right now. That's going to come later on. But in the end, electric potential to kinetic, and then kinetic to X-ray energy, which does have an equation that's we'll describe later on in the unit. All right, finally, gamma rays. Gamma rays are produced by nuclear decay. And what we really mean by nuclear decay is, yeah, matter is converted to energy. So we take a little bit of mass, and now it's gone. Poof, it's gone. But it hasn't just gone and exists as nothingness. Now it's gone and exists as energy. So energy is created by matter. That's Einstein, right? Einstein's theory of relativity equals mc squared. Energy is equivalent to mass. Okay, we'll talk about that equation later on in the year as well. All right. Given a frequency, we've got to be able to identify what type of EMR it is. Given a wavelength, given an energy, we have to be able to do the same thing. Let's say I gave you a frequency of 5 times 10 to the 15 hertz. What would it be? You might not remember right off the top, right? Okay. I got to think about it, actually, when I get a number like that. Somebody said it, though. Kessler, was it you? Okay. It is ultraviolet. And the reason we know it's ultraviolet is not because we've memorized the range of ultraviolet, but rather because we've memorized the range of microwaves to be 10 to the 9 to 10 to the 12 hertz. We've memorized the range of X-rays to be 10 to the 17 to 10 to the 19. And we've memorized visible light to be a little bit more specific here because it's a narrow range. 4 times 10 to the 14 to 7.5 times 10 to the 14. And the number that I gave you was, I think it was 5 times 10 to the 15, which falls right in between visible light and X-rays. We don't need to memorize the range of UV. We just need to memorize these three and then fill in the blanks for one, like I just gave you. What if I gave you a wavelength of 600 nanometers? That's 600 times 10 to the minus 9 meters, or 6 times 10 to the minus 7 meters. I don't see 10 to the minus 7 up there. Well, I don't even see wavelength up there. I see frequency up there, right? So what do we got to do? Get frequency, right? Get frequency. And to do that, we're going to say F is equal to V over lambda. This comes from the equation that you learned in Physics 20. We'll use this a lot more in Physics 30 as well, just not quite yet. V over lambda, what's the speed? What is it? Brielle, what were you saying? Speed of light, 3 times 10 to the 8. Is that the case for just visible light, or is that the case for all of them? All of them. They all have the same properties, except for frequency, and therefore wavelength and energy. Otherwise, they're the exact same thing. So the speed is the same. In a vacuum, all of these are 3 times 10 to the 8. The wavelength there is 6 times 10 to the minus 7. And when we do the math there, that works out to be 5 times 10 to the 14, which means what kind of EMR do we have? Visible light, yeah. Now, it would be very, very unlikely that you would have to identify which color of visible light. Okay? If you did, it would almost certainly be, say, like 4.1 times 10 to the 14, or 7.4 times 10 to the 14. Okay, if you have numbers like that, you can pretty safely say 4.1 would probably be red, right? And 7.4 would likely be violet, right? They wouldn't give you 7.3 and say, is it indigo or violet? They might give you 7.3 and expect you to know the difference between orange and violet, right? But 5 is almost in the middle there, right? What kind is that? I don't know, actually. I don't actually know. Okay. I'm going to guess it's going to be in that orangish, yellowish range, probably in the orangish range, but I don't know for sure. If I did have an option, though, orange or violet, we know it's orange, right? Just by some logic there, we would know it's orange. Orange or yellow? I'm not sure. So we shouldn't have to answer a question like that. Okay, does that make sense? All right. We had some questions for homework. All right, let's have a look here. Number 1 says, there's 2 ways that electromagnetic radiation is detected. We didn't review this, but one of the ways that EMR is detected is the way that Hertz detected it, right? Hertz had a really big potential difference across a gap. The electrons, as they jumped across that gap, accelerated, and that acceleration caused a changing electric and magnetic field, which caused, how did he detect it? What did he use to detect it? An antenna. What happened to the antenna when that changing electric and changing magnetic field hit it? Generated an electric current, right? So the detection of the current showed Hertz that, yeah, there was a changing electric and magnetic field, that it was caused by an accelerating charged particle, and that Maxwell's theory was correct. This is one way to detect EMR, right, is by using an antenna, using a radio antenna. Okay, you detect it every day if you turn the radio on in your car. It generates a current in the antenna. What's another way to detect EMR? I think I said, yeah, go ahead. Well, yeah, like there are some scientific ways that we just described, but there's also some more simplistic ways as well, right? If you turn on the microwave oven with food inside, and if it cooks, then, well, you've detected the presence of microwaves, right? Because your food wouldn't have cooked if there wasn't microwaves there. If you open your eyes and you can see, then you've detected the presence of visible light, because you wouldn't see if there wasn't visible light. Yeah? No? I'm not sure exactly what you're talking about. Those black? Sorry? Yeah, I don't know if that's... Yeah, nah, I don't think that would be there, because like it certainly detects heat, right? But that would be heat as a conduction thing, I think, taking place there, as opposed to like thermal energy being radiated. I think it's a good thought, but I don't think that would quite work for us. Anything that detects scientifically or every day any kind of EMR, right? Like you get a sunburn and your skin gets dark or gets reddish because of the sunburn. Well, you've just detected the presence of ultraviolet rays, right? So there's all kinds of ways that you can detect it. There's, like really scientific ways like Hertz's experiment, but there's less scientific ways as well. Okay, number 9. 9 says, what properties need to be considered when choosing a material to build an antenna for a radio receiver? I would actually change this question to say, what property really needs to be considered? It's the biggest property that needs to be considered. Yeah? It's got to be conductor. It's conductivity, right? The better the conductor, the better it's going to be. The size of it actually also matters, but it's the conductivity that they're really looking for here. The size of it matters because you want the size of it to be related to the wavelength of the wave that you're trying to detect. So that's going to be a factor. If you have too short of an antenna or too long of an antenna, it might not detect what you're trying to detect. But generally, we're looking at the material there, the conductivity of the material. 10, if the magnetic field lines held within a closed path are constant and unchanging, will there be an electric field in the closed path? Well, if you have a charged particle, there'll be an electric field, but is there an electric field that's as a result of the magnetic field here? Yes or no? Who says yes? Who says no? Okay, the answer is no. Good. How could we change this to change the answer to yes? Like, what small change or changes would we have to make to this question in order to make the answer yes, there would be an electric field generated? Yes, there has to be a changing magnetic field in order to generate an electric field. And that would generate a changing electric field. Constant electric field will not be caused by a constant magnetic field, but a changing electric field will be caused by a changing magnetic field. 12. Explain why it's necessary for the technician to leave the room or wear protective clothing when a patient is being X-rayed. I don't know about you, but when I was younger and didn't know anything about this stuff, okay, even when I was your age, like just before I was your age, right, in grade 10 or grade 11, before I learned about this stuff, I used to go to the dentist, and it always used to bother me that I go to the dentist, and they put this thing up to your mouth to take X-rays, and then the hygienist would say, "Okay, you ready? Like everything's good?" And I'm like, yeah. And then he or she would run out of the room, and then press the button. It's like, well, if this is not good for me, or if this is not good for you, then is it not good for me? Well, it's not good for me. It isn't. But X-rays are considered to be what we call ionizing radiation, as are gamma rays. And ionizing radiation does damage to healthy cells. Every time you get an X-ray, it does damage to your cells. But the body is remarkably good at repairing itself, to the point where generally, when we get an X-ray, our body can repair itself quicker than the damage is done. So we don't have to worry too much about getting an X-ray, right? But what's the problem with the hygienist or the X-ray technician? Repeated exposure, right? At that point, maybe your body can't keep up with the damage that's being done. My son earlier in the spring broke his jaw and got a lot of X-rays. Got a lot of X-rays around that time, and I was actually getting concerned about, obviously in addition to his jaw broken in 3 places, I was getting concerned about the X-rays that he was getting because they were taking a lot. And I actually asked about that, and the X-ray technician said that, I can't remember what the number was, but he would need a lot more X-rays than he was getting to cause any long-term damage to it. But the idea is, if you're an X-ray technician, like, you're going to be exposed to 40 or 50 of them in a day, right? Which at some point that's going to start building up, and your body's not going to repair itself. Last question, number 13. Describe how an antenna is affected by an EM wave. Quick, simple answer here. I think, who was it? I think Alex kind of gave it to me before. No, he kind of gave it to me, I think. Yeah. The fact that it has to be a conductor, which means that an electric current is generated in it, right? Otherwise, if you don't have a conductor, you don't have an electric current. If you don't have a current, then you don't need a conductor, right? So the two are integrally related to each other. You need to have a conductor, and an electric current is generated in it. Make sense? If you just have a constant magnetic field, then you're not going to generate a current, right? You need a changing magnetic field, which comes from electromagnetic radiation.